Alright, so our first section of calculus is going to revisit the concept of limits of functions, and we started talking about limits in our very first unit of the entire year, and it was kind of an introduction then, and we're going to just review that right now. So just to recap what you guys learned, I think it was part of your summer work actually, was that a limit is a value, so L would be the limit of f of x as x approaches c, if L is the value that the function becomes arbitrarily close to, which means it doesn't ever actually have to equal L, but the function gets closer and closer and closer and closer and closer to it as x approaches c. So just to give you an idea, say we've got a function here that looks like this. And in the beginning of the year, we talked about limits as x approaches infinity. And as x approaches infinity of this function, which would be farther and farther down here, this function would be getting closer and closer to the value of 0. So we talked about things like that, but we can also talk about at a specific value of c. Instead of c being infinity, what if c was 3? So what is our function, f of x, what is the value? Remember, the value of a function is just the y value. So what is f of x approaching as x gets closer and closer to c? Well, that would be whatever, this is our c, whatever y value that is. So let's say it's -1. So that would be the limit as x approaches c, or as x approaches 3 would be -1. So that's just a reminder, the limit of a function is the value that the function is getting very, 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 very close to as x approaches a specified value. And this whole unit is going to focus on finding limits. The easiest way to find a limit is by looking at a graph like we see here. You will not get a lot of problems like that because that's just very basic and pretty easy. What you guys are going to learn is how to evaluate limits by hand and analytically, and not using the graphs. But just so you guys understand what a limit is, we will go through those using graphs. So this limit right here in example 1, find the limit by completing the table. So one way to find limits is by completing a table. So what I want you to do is with your calculator, type in the function x minus 1, make sure you use your parentheses in the numerator and denominator, divided by x squared minus 1. So type that into the y equals. And we're going to use the table function on the graph, or on your graphing calculator. So once you type it in, I want you to hit the second button and then the window button. And what you're going to go to is the settings for the table. So what you're really selecting is table settings. And then if you look at the table setup on that screen, all that really matters is that if you go down to the second to last line that says independent, make sure your arrow is highlighting the word ask. So we want to ask the calculator to tell us the y values based on these x values on our table. So make sure ask is highlighted, and then hit second graph or the table button, and you'll see a table of values. Now you can type in 0.9 and hit equals, and you're going to be given a specific y value. So that specific y value is 0.5263. So let's write that in. Then type in 0.99 and hit enter. We get 0.5205. Now type in 0.999. We get 0.5003. So why are we choosing those values, 0.9, 0.99, 0.999? The reason is because we're looking for the limit as x approaches 1. So these values, 0.9, 0.99, 0.999, those values are getting closer and closer to the value of 1. So those three values take us close to 1. Now think about x approaching 1 from the other side, from above 1. Then we have these three values, 1.001, which is the closest one. So type that in, and we get 0.4998. And then we type in 1.01, so a little farther away. We get 0.4975. And then 1.1, and we get 0.4762. So as x is approaching 1, so let's say 1 is right here in the center. X is approaching 1 from this side, x is approaching 1 from this side. What is the y value of that function? So we can see the y value, if we approach from right below 1, it's 0.5003. From right above 1, it's 0.4998. What you're going to see is this will get closer and closer and closer to 1/2 on both sides. So using the table, we can see that the limit of that function as x approaches 1 is 1/2. So that's just one way we can figure out the limit of a function, by actually asking certain values of the calculator to tell us what the y value is as we get very, very close to whatever that value of c is. Okay, so everyone's favorite way to find a limit is just by looking at the graph, because you really don't have to think about it too much. You can just look at visually what's happening. So we'll practice doing that with the graph, just so you guys are, just to reiterate the idea of what a limit is. So here's our function, 2x plus 1. So if we graph that function, that's just a line with a slope of 2 and a y-intercept of 1. So hopefully you can think back and remember what that would look like. So it's got a y-intercept of 1 and a slope of 2. So I'll go up 2 over 1, up 2 over 1, down 2, left 1, and we've got, this line. So we want to know what is the limit of this function as x approaches 2. So here's our value 2, that's our value of c. What is that function approaching? Well, it's pretty basic and obvious that regardless of what side you're coming from, that function is approaching a y value of 5 as x approaches 2. For part B, if you're looking at this a little confused, it says the limit of f of x as x approaches 1. Well, what is f of x? Here's our function f of x. If you think back to when you learned about piecewise functions, this is a piecewise function that has two pieces to it. So the function for every single x value except x equals 1 is x plus 2, meaning it's a line with a slope of 1 and a y-intercept of 2. So I would go up 1 over 1, up 1 over 1, down 1, left 1. But before graphing that, when x equals 1, our function has a different value. So this little dot that I put right here isn't really a part of my line. So what I'll do is put a little open circle there to signify the fact that my line doesn't actually touch that value. I don't actually plug in x to the function when x equals 1, because when x does equal 1, my y value is 0. So here's the piecewise function. So this is asking what is the limit as x approaches 1. Well, we see that as x approaches 1, our function is getting closer and closer and closer to this y value of 3, but it never actually equals 3, because when x does equal 1, our y value equals 0. That's okay. The limit itself is the function, or is the value that the function is getting arbitrarily close to. Meaning, is there one single value that that function is getting closer and closer and closer to as x approaches 1? And the answer is 3. Even though when we plug in 1 to our function, we get 0 as the y value, the function itself is approaching 3 as x approaches 1. All right, this next example, the limit of 1 over x minus 2 as x approaches 2. Well, let's think about what this function looks like. First of all, if you plugged in 2 for x, you'd get 1 over 0, which is undefined. So this denominator, think all the way back to the beginning of the year, this function is undefined when x equals 2, which means in this case there's a vertical asymptote at y or x equals 2. And this function specifically looks like this, which you may not remember just by looking at it, but you'll get hopefully a good refresher on what some of these functions look like. The parent function of this, let me erase, I can't erase. Okay, the parent function is the function y equals 1 over x, which looks like this. And then this minus 2 just means the whole thing was shifted 2 in the positive direction, if you think back to translation. So that's what gives us this graph here. So the limit of our function as x approaches 2. Well, this one's a little tricky because as x approaches 2, x actually approaches 2 from from both sides, which it always will, but as x approaches 2 from over here on the left, as we get closer and closer to 2, what's our function doing? It's heading down to negative infinity. And then if we look at as x approaches 2 from the right, what's our function doing? It's getting closer and closer to positive infinity. So there is no specific value that our function is getting arbitrarily close to as x approaches 2. So in this case, this limit does not exist. So if you've ever seen Mean Girls, and you remember the scene where Lindsay Lohan says, the limit does not exist. This is one of those situations. Alright, so the limit does not exist if there is no one specific value that our function gets closer and closer and closer to. Okay, let's look at this next one, the limit of absolute value of x divided by x itself. So let's think about what this function would look like. First of all, I can't plug in the value of 0, which is where we're finding our limit as x approaches 0. But let's think about what happens as we put in the value of 1. Then our function would be, so here's our function. So if I plugged in 1, it would be absolute value of 1 over 1, which is just 1, so 1, 1. If I plugged in 2, it would be absolute value of 2 over 2, which is 1. If I plugged in 3, it would be 3 over 3, and so on. So this function looks like that on that side, and it will get, I can't plug in 0, but everywhere else besides 0, it's going to equal 1 for the positive values of x. Now think about what happens when I plug in a negative value of x. So if I plug in a negative value of x like negative 1, I'm going to have negative 1, and the absolute value is divided by negative 1. Absolute value of negative 1 is positive 1 over negative 1. So that y value is negative 1. Same thing with negative 2. Absolute value of negative 2 over 2. Oops, negative 2. That's going to be positive 2 over negative 2, negative 1. So you will see that this function, that half of the function looks like that, and it will get closer and closer to where x equals 0, but it will never actually equal 0. So this is the function of absolute value of x divided by x. We want to know what is the function approaching as x approaches 0. Okay, so as x approaches 0 from over here, my function is approaching the y value of negative 1. So we would think negative 1 would be the limit. But if we look at this direction, as x approaches 0, our function is approaching positive 1. So what we see is that there are actually two different values that our function is approaching as x gets closer and closer to 0. So the definition of a limit is one specific value that the function is approaching. So because it's approaching two different values as x approaches 0, then the limit does not exist. So DNE for does not exist. Alright, just a couple more examples and then we'll recap when we have limits and when we don't have limits. Let's graph this one, example E. So the limit of x minus 1 squared. So this one, first of all, I'm hoping that you'll remember by looking at the denominator that this function is undefined when x equals positive 1, because then I would get 1 in the denominator, or 0 in the denominator, which means we have, in this case, a vertical asymptote at x equals 1. The rest of this graph, you could graph it on your calculator or plug in a few values to see that our function looks like this. So when we look at the limit as x approaches 1, so we look at the limit as x approaches 1. From the right-hand side, we see it's approaching infinity. From the left, we see it's also approaching infinity. So this is going to seem a little confusing, but this limit, it is the same from both sides. It is approaching infinity. However, it's not a specific value. So because the limit the function itself isn't approaching, getting arbitrarily close to one specific value, this limit technically does not exist. So that's going to confuse some of you because a lot of you just want to say the limit is infinity, but infinity isn't an actual value. So the fact that it approaches infinity tells us that the specific limit doesn't exist. And then one other case where we're going to see this that a limit doesn't exist would be in this function here, the sine of 1 divided by x. Now, if you graph this in radians, you're going to see a really crazy looking graph that looks something like this. And what we find, we'll just kind of talk about it rather than really focus on the function itself. But if you zoom in closer and closer to what's happening as x approaches 0, because that's our value of c, this function oscillates, meaning goes up and down over and over and over infinitely many times as you get closer and closer to 0. So as you zoom in on 0, that function is just continuing to oscillate over and over and over. And because of that, it's never approaching a specific value, so that limit does not exist either. So just to recap, we saw how to find limits with graphs. If it's approaching the same value on that graph from both directions, then it's easy to find the limit. So these are the 3 types of behaviors where the limit does not exist. And the first one, what I just said, is if it's approaching a different value from the left and from the right, that limit doesn't exist. If it's increasing or decreasing without bound, meaning it's approaching infinity or negative infinity, then technically that limit, that specific value, doesn't exist. And then thirdly, we just saw if it's oscillating between 2 fixed points or at a certain point, the limit does not exist. So that's the general intro to limits. In class, we're going to look at how to find these limits without the graph. So I just want to make sure everyone has a firm understanding of what limits are by looking at the graph, so that when we're talking about them without the graph, we're still understanding the concept of what's going on. If you look down at definition of a limit, you see what looks like a foreign language. This is the epsilon delta definition of a limit. And while I would love to dive into this, this is something that we don't need to focus on this year. If you take Calc BC next year, you will dive into the formal definition of a limit. But it's basically just saying as x gets arbitrarily close to c, our function is getting arbitrarily close to a limit. And all of this looks crazy, and I get it. Don't worry about it. We're going to skip it for now, and if you're lucky enough to take Calc BC next year, you will learn all about this definition of a limit then. Alrighty, that's it for today.